Hello again, Dr. Jesse Key here. In this video, we examine chemical equivalence and number of signals in carbon NMR. A few examples of common alkyl and aromatic patterns will also be examined. Carbons which can be related by rotational symmetry are considered chemically equivalent and will appear as the same signal. Let's take a look at a simple example, propane, C3H8. The 3D ball and stick diagram provided shows the carbons of propane in gray and the hydrogens in white. If we rotate the molecule 180 degrees, notice that carbons 1 and 3 swap positions. This is an example of rotational symmetry relating these two carbons, making them chemically equivalent. Therefore, propane will have two signals total in its carbon NMR. A signal for carbon 2 and a signal for carbons 1 and 3. Carbons which are seen to be symmetrically related by a plane of reflection are also considered chemically equivalent and will appear as the same signal. Let's take a look at another simple example, isopropanol, C3H8O. Again, the 3D ball and stick diagram provided shows the carbons in gray, the hydrogens in white, and the oxygen in red. This diagram makes it easy to see there is a mirror plane running down the center of the molecule, relating the two methyl carbons by a plane of reflection. They are therefore chemically equivalent and will show up as one signal. A second signal would be observed for the central carbon. Therefore, a total of two signals is expected for isopropanol. In this slide, we'll examine the number of signals we would expect to find for some of the more common 3 and 4 carbon branched alkanes. Pattern recognition can help in the rapid interpretation of NMR spectra. Starting with the 3 carbon patterns, propyl groups have no symmetry relating the carbons, so we would see 3 signals, one for each carbon. Isopropyl methyls are chemically equivalent by symmetry, and therefore we would expect to see 2 signals. For the 4 carbon branched alkanes, we see 4 signals expected for both butyl and sec-butyl since there is no symmetry relating any of the carbons. Isobutyl would display 3 signals as the 2 methyl carbons are related by symmetry. Finally, tert-butyl has all 3 of its methyl groups related by symmetry, so only 2 signals are expected. The substitution patterns of aromatic rings affect the number of carbon-13 signals. On this slide, we have 3 constitutional isomers of the molecule dimethylbenzene, commonly called xylene, which we'll examine. The 1,4-dimethyl isomer produces 3 signals, as there are 2 symmetry planes shown as dashed red lines running vertically and horizontally through the structure. This makes all 4 ring carbons, highlighted in brown, chemically equivalent. The 2 ring carbons at the 1 and 4 positions are related by the horizontal plane of symmetry, and the 2 methyl carbons are also similarly related. The 1,2-dimethyl isomer produces 4 signals. There is a single plane of symmetry, which is shown by the dashed red line running horizontally through the structure. This relates each of the 4 carbons above with their reflected carbons below. Finally, 1,3-dimethylbenzene produces 5 signals. Similarly, it has a single plane of symmetry, which is shown by the dashed red line running vertically through the structure. This relates each of the 3 carbons to the left side of the plane, with their reflected carbons on the right side of the plane. However, the 2 centralmost carbons, with the plane running through them, are not related by symmetry and would appear as separate signals.